Hello everyone, this is Shovik. In this video, we are breaking down the important named reactions that you need to know whether you are preparing for NET, JEE, GATE, NET and any other competitive exams. So we will start with Apple reactions. In this reaction, it will convert this alcohol to the halide in presence of carbon tetrahalide and triphenyl phosphine as a reagent. Here halide will be bromine and chlorine. So reagents will be carbon tetrahalide and triphenyl phosphine. In case of 2-degree alcohol, this is 2-degree alcohol, it will react and it will give the halide with inversion of configurations in case of 2-degree and 3-degree alcohol. So now we will jump to the mechanism. Triphenyl phosphine will react with carbon tetrahalide. Here we are using carbon tetrabromide. So we have here phosphorus have one lone pair. This lone pair will attack on this carbon center and it leads to the removal of this bromide ion. So here bromide ion will leave, so it will form phosphorus bromide bond, and here carbon tetrabromide anion. This carbon tetrabromide anion will abstract the proton from the alcohol and it leads to the formation of the alkoxide ion, and this alkoxide ion will attack on this phosphonium ion and it leads to the removal of this bromide ion. Next will be, so it leads to the formation of phosphorus oxygen bond here, and this we have bromide in the system. So this bromide will attack on this compound on this intermediate and it leads to the inversion of configuration as I say into reaction. So this is a alkyl halide with inversion of configuration. Next reaction is Arbuzov reaction. It leads to the conversion of alkyl bromide to the alkyl phosphonate. This is alkyl phosphonate in presence of trialkyl phosphide. This trialkyl phosphide. Now we will go to the mechanism of this reaction. Triethyl phosphide have one lone pair on the phosphorus, and this lone pair will attack on this alkyl bromide and it leads to the removal of the bromide ion and it will form this phosphorus oxygen bond. Next we have bromide ion in the system. So this bromide ion will attack on this carbon and it leads to the removal of the ethyl bromide and it leads to the formation of alkyl phosphonate. So, and this is the starting material of our Horner-Wadsworth Emmons reactions, which is a type of Wittig reaction. It is a Wittig reaction. Next reaction is Arndt-Weissert reaction. In this reaction, it will convert the carboxylic acid into the next ion, carboxylic acid. So here one more CH2 group will be added in between the alkyl and carboxylic acid group. It will the reaction starts with the carboxylic acids. It will react with sulfonyl chloride in presence of acid and it will give acyl chloride, and this acyl chloride will undergo reaction with diazomethane in presence of diethyl ether to give diazoacyl group. This is a diazoacyl group. and this diazoacyl group undergoes uh, under this silver catalyzed reaction and followed by a hydrolysis reaction to give next had carboxylic acids. Now we will go to the mechanism of this reaction. So it will first start with the starting material, carboxylic acid. So here with this carboxylic acid, here this hydroxyl group have oxygen have lone pair. This lone pair will attack on the sulfur of the sulfonyl group, and it leads to the removal of the chloride ion. So it will form this intermediate, and this now in this reaction medium we have chloride ion. This chloride ion will undergo attack on this carbonyl, and it leads to the removal of this whole group. So it leads to the formation of this acyl chloride, and this acyl chloride undergoes reaction with diazomethane and it leads to the removal of this HCl, and it leads to the formation of this diazoacyl group. Now in presence of silver catalyst, this diazoacyl group will be present as in this form, or it will uh, or else it will be isomerized to like this to this form. So it here this anion will come here, so and a negative charge will come here, so it will form triple bond here, and it will here double bond will come here, so it will form anion. Next step, it leads to the removal of the nitrogen, and it leads to the formation of the carbon, and this carbon is a very unstable species. So this lone pair on the carbon will shift here, and this alkyl group will shift to on the carbon. So, and this so it leads to the formation of the ketene. This is a ketene, RCH double bond C double bond O, and later if we are reacting with this ketene with this H2O, so it leads to the formation of this next carboxylic acid. So this H2O will attack on this carbonyl group, and it leads to the and this double bond will shift here, and it leads to the formation of this next carboxylic acid. Next reaction is Baylis-Hellman reaction. In this reaction, this is a coupling reaction between this aldehyde or ketone between an aldehyde or ketone and activated alkene in presence of TAPCO as a catalyst. This is activated alkene because this alkene is activated by this carbonyl group. So that's why it is activated carbon. It is known as activated carbonyl. So it will give this coupling product. Okay. Now we will see the mechanism of this reaction. First, this TAPCO. First, this TAPCO have this is a DAPCO. So it have lone nitrogen here. Nitrogen have lone pair. So this lone pair will attack on this double bond, and it this double bond will shift here, so it will form negative charge here, and this nitrogen will be bonded to this carbon, and here positive charge. Next, this negative charge anion will attack on this carbonyl group, and it leads to the formation of this alkoxide ion. Okay, and next this alkoxide ion will take this hydrogen, and this bond will break, and this bond will break simultaneously. So it leads to the formation of this coupling product. Next is Barton-McCombie reaction. In this reaction, it will convert the alcohol to the alkane via this thiocarboxylate intermediate. This is a thiocarboxylate intermediate. Now we will go to the mechanism of this reaction. First we will start with the starting material, alcohol. So this alcohol will react with pyridine, which is acting as a base. So this pyridine will extract this proton of the alcohol, so it form this alkoxide ion. This alkoxide ion will react with this um, thiocar, like this is a like thionyl chloride. This is a thionyl chloride. So it leads to the removal of this chloride ion. So it will form this thiocarbonyl derivative or thiocarboxylate derivative. Next, we are using tributyl tin hydride. This tributyl tin hydride in presence of AIBN, like tributyl tin hydride, will present as this form. So AIBN, in presence of AIBN, this tributyl tin anhydride will this bond will break and it will form this two radical. So this tributyl tin radical will react here uh, with this sulfur, and it leads to the formation of a this radical, because this steps is possible because the formation of this strong sulfur and tin bond. This is the strongest bond. This is the strong bond. That's why this steps forwarded. Next will be this. This bond will break, and this bond will break. So it will form, and it removal of this whole residue, and it will form this alkyl free radical. This alkyl free radical will combine with the hydrogen free radical, which is generated here, and it will form this alkane. Our next reaction is Barton-McCombie decarboxylation reaction. In this reaction, it will undergoes the decarboxylation of this carboxylic acid to the alkane via this intermediate. So first we will start with this mechanism. First we will start with the starting material. Here in presence of DMAP, this hydroxyl will, DMAP is a base, so it will abstract this proton. No, not this way. So it will abstract this proton, and it will form this alkoxide ion. This alkoxide ion attack on the starting material, and it leads to the removal of the hydroxyl ion. Okay, so it will form this intermediate. After this, again we are using tributyl tin anhydride. Here tributyl tin anhydride will break down into the tributyl tin free radical, and it will, here this radical will attack on this sulfur, and it will form this a free radical. So it will form this free radical here. Next, it will this bond will break, and this bond will break. Okay, so it will leads to the removal of the CO2, and it leads to the formation of this free radical intermediate. This free radical alkyl will recombine with the hydride free radical, so it will form this alkane. Next is parchment recyclation. In this reaction, it leads to the cyclization of this ine, ene, this is ene, and diene to the substituted arenes under the thermal or photochemical conditions. So we will see the mechanism of this reaction. So first it will start with the starting material in diene. This is in diene. In presence of heat or photochemical condition, this bond will break uh, in a this bond will break into two radicals, and these two radicals will recombine to a bond. So it will form one bond from here to here. So it will form a 6-membered ring: 1, 2, 3, 4, 5, and 6. So it will form the two like a diradical. It will form this diradical in presence of cyclohexadiene. This is cyclohexadiene. This radical will abstract this proton like this way, and this will form a free radical here, and this bond broken into this, and it will recombine here. So it will form like this. Okay, so it will here hydrogen will come here. Next, again this free radical abstract this proton, and it leads to the formation of this aryl derivative. This is the aryl derivative, and here it will form as cyclohexene. Cyclohexadiene will convert it to the benzene. Next reaction is Buchwald-Hartwig amination. This is a palladium catalyzed coupling of the aryl halide with amine, like here amine. Here that amine will be 1 degree or 2 degree, and it will produce aryl. It will produce aryl amine in presence of palladium catalyst. So we will see the catalytic cycle. So first we will start with the palladium catalyst. Here palladium catalyst is present in the zero oxidation state. Okay, so first this aryl halide undergoes oxidative addition, and it leads to the formation of the palladium 2 species. And next, in presence of sodium tert butoxide, it leads to the removal of the sodium halide, and this halide will go, and in presence in this place OTBU will come because of this base. Next, in presence of the amine, that is 1 degree or 2 degree amine, it will undergo transmyelination, and it will give tert butanol. And here in presence of OTBU, here it will come NHR dash. And next step is the reductive elimination, and it leads to the formation like these two will form bond and remove from the system, which is known as reductive elimination. And this due to the reductive elimination, the palladium 2 will reduce to the palladium 0. Next reaction is Blaze reaction. This is a zinc mediated reaction of nitrile with alpha haloester to produce beta enamino or beta ketoester. this is nitrile, and this is alpha halo. This is alpha bromo, which is same as alpha halo, alpha bromo ester. And presence of zinc, it will form this beta enamino ester. And in present, if we will do hydrolysis in presence of acid, if we will do hydrolysis, it will form beta ketoester. Now we will see the mechanism of this reaction. So first, this alpha bromo ester will react with the zinc to form this organozinc compound. This organozinc compound will react with the nitrile nitrile group, like it will react on this nitrile carbon. Here this is minus and this will be plus. So here in my so minus will, so this carbon will attack on this carbon, and this this bond will break down to here. So it will form this R C double bond N, and it will be bonded with this CH, this ester group, CH, then ester group, and it will be here this nitrogen will be bonded with and ZnBr, so it will be shown here. So in presence of potassium carbonate, it will form this beta enamino ester. In presence of acid, if we do hydrolysis of this intermediate, so it will give beta ketoester. Next we'll see the two reactions at a time. Here for two reactions, starting material will be same, and just there will be change in the reaction conditions. So first we will see here this ketone. This is a ketone. So if we will react this ketone with the tosyl hydrazine, this is tosyl hydrazine. This tosyl, in presence of tosyl hydrazine, it will form this tosyl hydrazone, because and the this reaction happens like this. It will form a bond, double bond, instead of double bond O, here N, single bond NH and TS, and it leads to the removal of the H2. So it will form this tosyl hydrazone. Now this, from this tosyl hydrazone, two reaction will do. We can do like one is Shapiro reaction, another one is Bamford reaction. Now we will see the Shapiro reaction first. So in case of Shapiro reaction, we are reacting this tosyl hydrazone with two equivalents of n-butyl lithium. So this n-butyl lithium will act as a base. So this two equivalents of n-butyl lithium will abstract this proton and this proton also. So it will form here anion, dianion it will form, and later it will later like like this double anion will come here, it will be shifted here, and this double bond will shift here, and it leads to the removal of the tosyl anion, and it leads to the formation of this anion. Next, it leads to the removal of this nitrogen. So it will form this anion, and in presence of H plus, so because H plus will be there in the system. So it will abstract this hydrogen and it will form this alkene, which is a less substituted alkene. But in case of Shapiro reaction, it will form less substituted alkene. But in case of Bamford reaction, it will form more substituted alkene. So now we will see the Bamford reaction, Bamford-Stevens reaction. In case of Bamford-Stevens reaction, we are using sodium methoxide, which is a very weak base. And in case of Shapiro reaction, we are using very strong base, that is N-butyl lithium. So this in sodium methoxide, and we are acting as a weak base, and we are using it only one equivalent. So this will abstract this methoxide will abstract this proton, and it leads to the formation of this anion. So there will be two conditions. After this, there will be two conditions. One will be in presence of acid, and in absence of acid. First, we will see this is the in presence of acid. This is in presence of acid. So in presence of acid, this anion will this in presence of acid, this anion will come, this negative charge will come here, and this bond will be shifted here. Like this bond will be it will form this bond will come here, and it will take one H plus, and it will form this N double bond in TS. So, and next step will be leads to the removal of this tosyl ion, and it will form this next and the next step will be removal of the nitrogen ion, and it will form this carbonium ion, and this carbonium ion, and in the next step it leads to the removal of this H plus ion, and it leads to the formation of more substituted alkene. And under the aprotic solvent, like under non-acidic conditions, so it will form, so it will there will be no H plus will be there. So so negative charge will come here only, it will not take any H plus. So it will come here only, and it will not take any H plus. Next step, it leads to the removal of this nitrogen and tosyl. So it will form this carbene. Now this carbene will undergo the hydrogen insertion reaction. It leads to the hydrogen insertion reaction, that is this double carbon lone pair will take this hydrogen, and it leads to the removal of this hydrogen, and it leads to the formation of this alkene. So it will form this more substituted alkene. Next will be the cope elimination. In the cope elimination, it is a thermally induced seen elimination of cope, seen elimination of N oxides to an alkene. First, we need to prepare this N oxide. That is, this is the N oxide. First, we will prepare from the amine by oxidation with MCPBA. So it will form this N oxide. And next, it leads to the, if we heat this N oxide, then it leads to the formation of this alkene. So how it will form, like here it will undergo only seen elimination, only like you see here this this oxygen and this oxygen and this hydrogen will be in the same plane, so it will undergo the elimination. So this anion of this oxygen will abstract this proton, and this bond will break, and this bond will break. So it leads to the removal of the NH NOH into. At the same other hand, in this reaction, like here, this oxygen have two. We have two hydrogens here, which have in the same plane to the hydrogen. So it will form two product. Like it will abstract this proton also, and it will abstract this proton. So if it will abstract this proton, so it will form like this. So it will abstract this proton. So it will abstract this, and it leads to the removal of this NMe2OH. So it will form two product. One is this alkene, and another one is this alkene. Next is a click reaction. This is a 3+2 cyclization of substituted azide. This is a azide, substituted azide with alkyne, and it leads to the formation of the triazole. This is a triazole. This is a full substituted triazole. So there will be two catalysts will be there, that is ruthenium catalyst and copper catalyst. In presence of copper catalyst, it will give 1,3 disubstituted triazole, that is here 1 2 3, and in presence of ruthenium catalyst, it will undergo 3+2 cyclization to give 1 2 disubstituted triazole. So how it will happen, like 3+2, how it will happen, this here this 3+2 happens like this carbon, this anion will come here. This anion will attack on this carbon, and this triple one bond of the one single bond of this triple bond will attack on this nitrogen, and it leads to the removal of this double bond. One bond of this double bond will shift to this nitrogen cation. So it leads to the formation of this 1,3 disubstituted triazole, same as like this also. Action. This is a intramolecular thermal or Lewis acid catalyst reaction between the unsaturated carbonyl compound to yield cyclized products. This is a intramolecular unsaturated carbonyl compound. This is a double bond, that is why this is unsaturated carbonyl compound. In presence of heat or Lewis acid, it will form the cyclized product. Now we will see the mechanism of this reaction. So we will start the mechanism. This lone pair will attack on the Lewis acid, and it leads to the formation of the O plus and AlCl3 minus. Next step, this hydrogen will it will undergo isomerization to form this intermediate. Next step will be the cyclization, and cyclization will happens like this bond will shift here, this bond, so that's why this bond will come here, and here negative charge, and this negative charge will come here and abstract this AlCl3, and followed by removal of this bond, and it leads to the formation of this product intermediate. Now in presence of acid, it leads to the removal of this AlCl3, so it will form this this product like this anion, and this anion will abstract the proton, and it leads to the formation of this product. Next is Koresh-Schabowski reaction. This is a reaction of sulfur halide with carbonyl compound to give epoxide, and in case of alkene it will give cyclopropane. So this is a sulfur halide, because sulfur halide means sulfur will be positive charge and carbon will have negative charge. Where carbon is negative and sulfur is positive. So here positive and this is negative. So and this is in case of carbonyl, oxygen is negative and carbon is positive. So this minus will attack on this. So this is a minus, carbon is minus, so carbon will attack on this this carbon, and it leads to the formation, and this double bond will shift here, and it leads to the formation of this alkoxide, and its bond is attached to CH2 SME2 plus. Now this anion will attack on this carbon, and it leads to the removal of this DMS, that is dimethyl sulfide, that is Me2S, and it leads to the formation of this epoxide. In presence of now, if there is any alpha beta unsaturated carbon is there, alpha beta unsaturated carbon is there, like this alkane, in presence of this stabilized sulfoxonium anion, sulfoxonium halide, like here, this is here one, this is a stabilized halide. So in presence of this halide, it leads to the formation of this cyclopropane. So how it will form? So this is a alpha beta unsaturated in carbon and carbon. This will be present as sulfoxonium and CH2 minus and S plus. This minus will attack on this carbon, and this bond will shift here, so it leads to the formation of R, here minus a double bond CO R dash. Okay, so here it will be attached to CH2, then S double bond O Me2 plus. Next step will be this carbon ion will attack on this carbon, and it leads to the removal of this DMSO. So it will form this cyclopropane with the removal of the DMSO, and in presence of unstabilized halide, it leads to the formation of the epoxide. Here this halide will react with the with this carbonyl group, not with this alkene. So it will form this epoxide. Now Corey-Fools reactions. In this reaction, it leads to the conversion of aldehyde to the terminal alkyne. That's aldehyde to terminal alkyne. So first alkyne, and this aldehyde will react with the triphenyl phosphine and carbon tetrabromide. It leads to the formation of the dibromide intermediate. This dibromide intermediate and reacts with two equivalents of N-butyl lithium, and followed by hydrolysis to give terminal alkyne. Now we'll go to the mechanism of this reaction. This triphenyl phosphine will react with the carbon tetrabromide. Triphenyl phosphine have phosphorus have one lone pair, so this lone pair will attack on the carbon and it leads to the removal of the bromide. Okay, bromide ion. And so it will form this PPH3 plus bonded with CBr3. Now we have bromide ion in the system. So it will form like the here bromide will attack on this bromine and it leads to the formation of this halide, that is phosphorus halide. PPH3, it leads to the formation of this PPH3 double bond C, CBr2. Now in presence of aldehyde, in presence of aldehyde, it will undergo the Wittig type of reactions, so it will form this dibromo intermediate. Next, this dibromo intermediate that will react with the n-butyl lithium to give this terminal alkyne with a bromine bromo terminal alkyne with a bromo derivative. This n-butyl lithium will abstract this proton and it this bond will break and this bromine will removes, so it will form this alkyne derivative. Next, in presence of another equivalence of n-butyl lithium, it will undergo lithium halogen exchange. So in presence of this n-butyl lithium, this bromine will exchange with lithium, so here Cl bond. Next, in presence of H2O, this organolithium compound will convert it to the alkyne, and in presence of any other electrophiles, it will here this lithium will be exchanged with in that electrophile. Next is co-raking oxidation. It is used to oxidize 1 degree or 2 degree alcohol to the aldehyde or ketone respectively. This is the 1 degree alcohol and this is 2 degree alcohol. Now in these reactions we are using the reagents like DMS, and that is dimethyl sulfide. This is DMS, dimethyl sulfide, and NCS, that is N-chlorosuccinamide, and triethylamine as a base. Now we'll start the mechanism of this reaction. We'll start with NCS, that is N-chlorosuccinamide. This is N-chlorosuccinamide. Now this DMS, that is dimethyl sulfide, sulfur have one lone pair. This lone pair will abstract this chlorine and it leads to the formation of this anion, that is and this leads to the formation of this anion and this chlorosulfonium ion. Now this chlorosulfonium ion will react with our alcohol. This we have alcohol have a hydroxyl group. In this hydroxyl group, oxygen have lone pair. This lone pair will attack on this chlorosulfonium ion and it leads to the removal of this HCl chlorine, and overall HCl, it will remove HCl, so it will form RCH2O, then bonded with sulfur, this bonded with sulfur. Now in presence of base, that is triethylamine, it will abstract this proton and this bond will break and this bond will break and it leads to the formation of aldehyde. And in the absence of base like triethylamine, so there will be no base, so we in our reaction medium we have chloride ion, so chloride ion will attack on this intermediate and it leads to the removal of this full DMSO, so it will remove the DMSO and it leads to the formation of alkyl chloride. Next is core winter synthesis. This is used to convert the syn diol to alkene. So it will in presence of syn diol, in presence of this phosgene. This is phosgene and triethyl phosphate, and we need to add give heat, then only it will give this alkene. So in presence of different alcohols, it will give different alkene. Okay, now we will see the mechanism. This is the syn diol, so we don't need to do anything. This is a syn diol, so it will form, it will react first with this phosgene first, and it will form this thiocarboxylate intermediate. Okay, because here two hydroxyl are in syn, so we don't need to do anything here. Here this R and this R dash are in anti position, so we are giving like both are trans to each other. Now we have triethyl phosphate, so this triethyl phosphate have phosphorus has lone pair, so it will donate its lone pair to the sulfur, and this bond will break to form this anion. Here this anion will form, and it's bonded with sulfur with phosphorus plus. Next next will be like it will lead to the removal of this like breaking of this bond, and its leads to the formation of this carbene. This carbene are electron deficient species, so again this triethyl phosphate will attack on this carbene, and this leads to the formation of this zwitter ionic species. This zwitter ionic species will undergo cleavage, that is here this bond will come, this bond will cleave, this bond will cleave, and this bond will cleave. So it leads to the formation of CO2 and PO ETR whole thrice, and this E alkene. Here it will form the E alkene because both R and R dash are in trans to each other. Now in case of this alcohol where both are trans to each other, so in this case it will not react easily, so we need to convert this conformation to the trans diol to the cis diol. So first we need to convert this structure to Newman projection. Here both R and R dash is on trans to each other, and both hydroxyl group are trans to each other. Now we need to do 120-degree clockwise rotation. If we are doing 120-degree clockwise rotation, so this R, so this hydroxyl group will, no, this hydrogen will come here, this R dash will come here, and this hydroxyl group will come here. So it will form this configuration. Now we need to convert again this to this configuration. So in this case you see both R and R dash in the syn, they are not in trans, and both hydroxyl group in the syn position. So now it will react with the phosgene, and it leads to the formation of this thiocarboxylate thiocarboxylate intermediate. In this case both R and R dash are in syn to each other, so after reaction with the triethyl phosphate, and in presence of heat it will give Z alkene, because here both R and R dash are seen to each other. Next reaction is Darkin reaction. It allows the preparation of aryl alcohol from aryl aldehyde or aryl ketone via oxidation with H2O2 in presence of base. So this is aryl aldehyde in presence of H2O2, and that is a hydrogen peroxide and base. We are using sodium hydroxide as a base, so it will give aryl alcohol, and in case of ketone, it will also give same product. So we will start the mechanism of the reaction. This hydroxyl group will abstract the hydrogen of the hydrogen peroxide, and it leads to the formation of hydrogen peroxide anion. This anion will attack on the carbonyl group of the aldehyde, and this bond will shift here. It leads to the formation of this alkoxide ion. This alkoxide ion will abstract the proton from the system, so it will form this intermediate. Next will be like this bond will break, and this bond will break, and this phenyl will shift here, shift to the oxygen, and it leads to the removal of the hydroxyl group. This is hydroxyl group. So here it will form like phenyl with oxygen COHO, and in presence of hydroxyl group it will attack on the carbonyl group, and it leads to the removal of the it leads to the formation of this alkoxide ion. In presence of acid, like it is also acid, it will form this alcohol. Okay. There will be same mechanism for the ketone also. Now in case of Darzin reaction, next reaction is Darzin reaction. This is a condensation of carbonyl compound with alpha haloester in presence of base to produce alpha beta epoxy ester. Like this is a alpha and beta epoxy ester. So we will see the mechanism of this reaction. First we'll start with alpha halo ester. This is alpha halo ester in presence of base, that is potassium tert-butoxide. It will abstract this proton, and it leads to the formation of this anion. This anion will react with this carbonyl group, and now it will give the two diastereomer, where this halide and this alkoxide ion will be on same phase, or this halide or this alkoxide ion will be on different phase, like opposite phase. If when both halide and in this case both halide and oxygen and alkoxide ion on the opposite phase, so it will undergo SN2, that is NGP type of reaction, and it will form this epoxide. And in case of where the both alkoxide and epoxide are both alkoxide and this halide are in same plane, then it will we need to do CC bond rotation. So then only it will form this both this halide and this alkoxide will be on different phase, like opposite phase. Then only this NGP will happen. So it will undergo NGP, so it will form this epoxide. So it will form two products. In this reaction we are getting two products, that is two diastereomers. Now we'll see the Days-Martin oxidation, that is DMP, which is known as DMP oxidation. It will help to oxidize the 1 degree or 2 degree alcohol to an aldehyde or ketone respectively by using the DMP reagent. This is a DMP reagent. DMP means Days-Martin periodinane. Now we will see the mechanism of this reaction. This alcohol will react on um, this alcohol lone pair, oxygen lone pair will react on the iodide, that is iodide of the DMP, and it leads to the removal of this acetate ion, that is it leads to the removal of acetate ion, and it will form an H plus ion, and it will form this bond, oxygen and iodide bond. Next step will be this oxygen CO bond will break and abstract this proton, and this bond will break, and this bond will break and simultaneously, so it will form this aldehyde, and same mechanism will follow in case of 2 degree alcohol, which will form this ketone. So next will be Dickman condensation. This is a base catalyzed intramolecular condensation of a diester. This is a diester. Leads to the formation of beta keto ester. This is alpha. This is beta. Beta. This is beta keto ester. So mechanism, now we'll see the mechanism of the reaction. So this is the diester. In presence of as base, it will abstract the proton, and this leads to the formation of the anion. This anion will attack on this carbonyl group of the ester, another ester, and this leads to the formation of cyclized product. So it will form 1, 2, 3, 4, 5, 6 membered ring with which is a beta keto ester. This is beta keto ester. Enine metathesis. This is a ruthenium catalyzed metathesis reaction between alkyne and alkene to produce the 1,3-diene. This is 1,3-diene. This is alkyne in presence of ruthenium catalyzed metathesis reaction. This is a Grab's catalyst, which is known as Grab's catalyst also. This is a Grab's catalyst. In presence of Grab's catalyst, it will form this 1,3-diene. 1, 2, 3. This is 1,3-diene. So now we will see the mechanism of this reaction. First, this alkene undergoes reaction with the undergoes 2+2 cyclization with this ruthenium carbene complex. This is a ruthenium carbene complex to form this cyclobutane type of intermediate. So it will form this like this 2+2 cyclization to form this cyclobutane type of intermediate. Okay, next step is will be it leads to the no, it leads to the breakage of this bond like this way, and it leads to the removal of the CH2 double bonds in the CHR double dash, and it leads to the formation of this carbene, ruthenium carbene. This is a metal carbene. Now it will in presence of alkyne, it will again undergoes 2+2 cyclization to form this cyclobutene type of intermediate. Now again it will undergo this ring opening reaction. So it will goes by this, it will break this bond, and it will break this bond. So it will form R dash C double bond C ruthenium is. And again, in presence of CH2, we have this in the system. We have this this alkene, that is CH2 double bond CHR double dash. It will undergoes 2+2 cyclization to form this cyclobutane type of intermediate. Now it will undergoes ring opening reaction again. So it will undergoes ring opening to form this 1,3-diene. Now this is another, like this is an intramolecular enine metathesis. First same as like 2+2. In this alkene will undergoes and 2+2 cycloaddition with this ruthenium carbene complex to form this metal carbene complex like this. Again, now this this metal carbene complex will react on this with this triple bond, and it will form this type of cyclobutane type of intermediate. And next step will be ring opening reaction. So it will form this here double bond, and here double bonds are ruthenium alane. Next it will react with this CH2 in the reaction medium. CH2 double bond CH R dash will be there, so it will give this cyclobutane type of intermediate. Next step, it will undergoes this ring opening reaction to give this 1,3-diene intermediate, 1,3-diene as a product. Next reaction is Eisen-Weyler-Clark reaction. This is a preparation of 3-degree methylamine from 2-degree amine and formaldehyde in presence of formic acid. This is 2-degree amine and this is formaldehyde, and in presence of formic acid it will give 3-degree methyl amine. This is 3-degree amine. Now mechanism of this reaction is formaldehyde oxygen have lone pair, so it will abstract proton of the acid, formic acid, and it leads to the formation of the cation. Now this in case of 2-degree amine, it have one lone pair on the nitrogen, so this lone pair will attack on this carbon, and it leads to the breaking of this CO double bond, and it leads to the formation of this intermediate. Next step is now this hydroxyl will have one lone pair, so this lone pair will abstract this proton, and this leads to the formation of OH2 plus. Next step, this lone pair on the nitrogen will shift like this way, and it leads to the removal of this H2O. So it will lead to the formation of iminium ion. This is a iminium ion. Next step is, like we have in the step in the first step, like it will lead to the formation of this carboxylate ion. So this carboxylate ion will react with this one, so it will react like, and this anion will come like the anion will shift like this way, and this hydrogen hydride will attack on this attack on this CH2, and it will shift, this bond will shift to the nitrogen cation, and it leads to the formation of 3-degree amine. Next is Hale-Bollard-Zielinski reaction. This is an alpha bromination of carboxylic acid, which is catalyzed by red phosphorus. This is alpha. This is a carboxylic acid, so it will undergoes the alpha bromination. This is alpha position. In the alpha position, it will undergoes bromination in presence of red phosphorus. So first we will see the mechanism of this reaction. This phosphorus will react with bromine to form this phosphorus bromide, like that is PBr3. This phosphorus bromide will react with 3 molecule of this carboxylic acid to form this acyl bromide. This acyl bromide will undergoes it will undergoes ketoenol tautomerization to form this ketoenol form, and this enol form will react with the bromine, and it leads to the formation of alpha bromination. Now this alpha bromoacyl bromide, this is alpha bromoacyl bromide. Alpha bromoacyl bromide will react with another molecule of this carboxylic acid to form this alpha bromo carboxylic acid plus 1 mole of acyl plus acyl bromide, and again this acyl bromide will react the same way as before. Next reaction is Henry reaction, and this is a base catalyzed CC bond formation reaction between the nitroalkenes and aldehydes or ketones. This is a nitroalkane, and this is a carbonyl group. In presence of base, it will undergo CC bond formation reactions. So now we will see the mechanism of the reaction. So nitroalkane have one proton, acidic proton. This is an acidic proton. Base will abstract this acidic proton, and it will form this anion. This anion will attack on the carbonyl group, and this leads to the formation of this alkoxide ion. This alkoxide ion will abstract the proton associated with the base, so which will be abstracted before, like here B minus will abstract the proton, and it will form BH, and this BH will be used here. So it will form this CC bond. So it will form the CC bond. It will form this coupling product, like condensed product.